Hello. Yeah, we'll get started in 5 minutes. Yeah. Um, I know it's 9 o'clock, and thanks for making it at time. We'll just wait for another 5 minutes, just hoping to see a little more people here. Yeah, thanks. Good morning, everyone. Uh, Welcome to the IEEE Nanotechnology Workshop. Are you all excited to be here? We are too. So we have a jam-packed two-day event for you. This event has been sponsored by Airbus and our department Sense. So we have, I'll just go through the schedule, you all have it. We wanted to have something like lecture, training, and industry kind of a thing all together on one platform. So first session will be starting with 4 lectures where they will show you the different processes and tools in fabrication, characterization, and packaging. And then we will have tours to the clean room, the characterization facility, photovoltaics lab, packaging lab, and functional thin films lab. And we have an industry session, 2 industries, Centum Electronics and Airbus. They will be coming and talking to you about what they do and what they expect to see in students when they maybe give a project or recruit you. Yeah, that's about it. And we'll get started. So session 1, Dr. Gopal Hegde will be chairing the session. He is the chair of the IEEE Nanotechnology Council for the Bangalore chapter. Sir, please welcome to chair the session.
Good morning. First of all, I welcome all the participants coming, I think, all over the country. It's a good indication that within a short notice, you are able to make it. And as she explained, the session starts with the first talk by Professor Rudra Pratap. We all fondly call him as RP. He's our chairman. So I give a brief introduction. I think in any nanotechnology meetings across the country, I think he's well known. I need not have to give a big introduction, but very short introduction without stopping the talk. I'll just make it. Professor Rudra Pratap is the chairperson of the Center for Nanoscience and Engineering currently, and an associate faculty at the Department of Mechanical Engineering, IISc. His research interests include MEMS and NEMS, sensors, transduction, targeted material development, energy dissipation in oscillations of micro and nanoscale structures, vibratory mechanobiology, etc. And more than that, I think he has been working on. Professor Rudra Pratap holds a PhD degree from Cornell University, USA, master's degree from University of Arizona, USA, and BTech from IIT Kharagpur. He has been at the Indian Institute of Science, Bangalore, since 1996, and he has the lot of credentials for bringing up this center. I think he will be talking on MEMS sensors. Professor Rudra Pratap.
Thank you, Dr. Hegde, and thank you, Nilima, for giving me this opportunity to talk to this wonderful audience of young and enthusiastic people. For professors, there is no better pleasure than to teach a class of interested students. So here we are. I'm interested in teaching you something about MEMS, and you have traveled far and wide. I hear that people are here from corners of the country as far as Gujarat, or somebody from Jammu and Kashmir and Assam. Amazing. So first of all, thank you so much for taking this trouble to come all the way here. And we hope that whatever we are going to do now is worthy of your effort. That the trouble that you have taken to come all the way here. So in a second we will yeah, accept that. So Nilima, we are starting at 9:10, and how much time have you allocated to me? 45 minutes. Okay, fantastic. So up to 10 o'clock you are mine, all right? Okay, very good. So let's look at the world of MEMS. What I want to talk to you about is this world, this fascinating world of MEMS sensors. And I want to take you all the way from, perhaps basics to the excitement that the world is facing today, okay? So that many of you who don't have any exposure to MEMS should also get something out of it. How many of you have not heard of MEMS? Anybody here? And it's not a crime to raise your hand, say, hey, what is MEMS? I don't know about it. Okay, only one person. Only one person. How? Okay, a few people. Very good. So slowly, you don't have to be so hesitant. We are not going to grade you at the end of this class. Okay? So don't worry. Just raise your hands. So this is micro electromechanical systems. You know, this is where mechanical systems get married to electronic systems, and it's a real marriage. You will see that, you know, it's a real marriage, and I'll tell you why we call it real marriage. Because even the mechanical structures are made the same way that electronic components are made. They both use the same CMOS process. They both use the same materials, and therefore all of a sudden mechanical engineers or people who know about mechanics, aerospace engineers, civil engineers, they all find themselves awestruck that, oh, it's the same beam that I know throughout my life, but now it is made of silicon. Now silicon is not something that you use for structural material to make, you know, beams here. You use silicon oxide inside, but you know, you don't use silicon per se, right? And the structures that you make are not so small, and therefore now all your intuition that you have at macro scale doesn't hold good anymore. So you feel insecure. Electronics engineers who know the process very well, who know the materials very well, all of a sudden find that they are not making transistors. These are not devices which are sitting inside the substrate. Okay, they are floating, they are moving, they are vibrating. What's going on? This is something we left in the first year of engineering. So they feel insecure that, all of a sudden there is something new, and therefore you make rapid progress in this area only if both of these work together. And this center is an embodiment of that. We have faculty members from all disciplines here at the center. I am from mechanical engineering. My colleague Professor Naukant Bhatt from ECE, from electrical communication engineering. There are several other faculty members from electronics, physics, material science, and that's how things like this get created, and that's how you work in these areas, right? So it's a beautiful interdisciplinary area. So let's see, I'm talking about shrinking sensors and exploding applications. Okay, sensors are going down in scale, they are becoming very, very small, and applications are exploding like nobody's business. I'll convince you in a minute. So we will talk about why do we need multitude of sensors. Okay, that's one thing I'm going to talk about. Why there is so much need that if this room was replicated 1,000 times, you know, with all of you sitting, I can engage the entire audience in this one discipline of making sensors, okay, and I'll convince you of that. Why we should look at MEMS to do this multitude of sensors? What is sensor technology? What is the infrastructure required to work in this area? What is the current state of MEMS sensor development in India, and future of MEMS sensors? Okay, that is something futuristic I'll tell you about. So you hear of, you know, you are sick of hearing of smart things, aren't you? You know, smartphone, smart this, smart that, smart city, smart bus, except for human beings. Everything else seems to be getting smarter. Right? So what do we mean by this smart world or a smart city? All of this smartness that we talk about. So if you think about it, or if you read about it, you know that people are talking about all interconnected devices which are talking to each other. Sometimes with your help, sometimes with your interference, and sometimes autonomously. They know what to talk to each other about, right? So how do you talk to each other without having some smartness to know that I should talk to you, right? What should I talk to you about? Why should you care? I want to talk to you, right? In all of this you realize that the basic element is all of these things must be able to sense, right? Must be able to sense. all of you young guys suffer from something called love. Everybody suffers, but you know, young people in larger quantity. So all of you have experience of looking at somebody who doesn't want you to look at them, right? So you need to read those sensors and say, oh, not compatible signal, move away, right? So this is important, that sensing is at the heart of smartness. Say you are the same human being and somehow I zap all your sensors, all your sensing capability. You can't see, you can't hear, you can't taste. What do you become? You know, the entire body full of all the machinery, I just take away the sensing capability. You are reduced to nothing, right? Absolutely nothing, useless, completely useless. You have hands, legs, everything, but it can't work. Okay? Neurons are not firing because they don't have feedback signal. There is no sensory input and therefore it all stops. So now we are talking about this smart world based on just this thing, that all of these elements of the world can sense their environment and can communicate, can actuate things. That's the whole premise. So if you, now you are talking about the world, break it into smaller pieces and look at what smartness is required at what level. So you have personal requirement, you have local requirements for, you know, this building to be smart, it should have something in it. I will give you examples of that, cities requirements and nations requirement, and then you agglomerate all of that and that's your smart world, correct? So smartness has to be imparted at all levels. Now let's see what what if we really want to make this smart world smart, what is the requirement of sensors? I am going to go into some details of what kind of sensors are we talking about, but just now, you know, for now you just focus on this idea that everything will require smartness and therefore everything will require sensors. Okay? Think of natural things, you are full of sensors. Okay? As a matter of fact, it's amazing that the wrapper on you, the packaging material that the nature has used on you, which is called skin, the skin has 60,000 sensors in it. Even the wrapper, inside there are billions of sensors, right? So that's the kind of, take a small insect that also has sensors, not as many as you have, but they have sensors too. So sensors will be required everywhere. Now if you map that to buildings, roads, you know, signboards, buses, trains, you will need trillions of sensors. So here is a forecast which says that in another 15, 20 years, we will need 45 trillion sensors in the world working. 45 trillion. Now I know that all of you are smart people, you know how to do exponents, but that doesn't do anything. Okay? 10 to the power, you know, what is it, 9, 12, but beyond a certain number, those exponents just become numbers. You don't have feel for it, right? Like you know how much is 1 lakh rupee, right? You know that. You stretch a little bit, you know some rich friend, so 1 crore, you know how much is 1 crore. But now if you, somebody says 1 Arab or 1 Kharab or these units, you know, billions, trillions, do you know how much money that is? No. You only know number of zeros. You don't have a feel for it. You understand? Feel for it. But engineering is not done just by numbers. Engineering is done by feel, gut feel. Okay? All those numbers have to make their way into you so that you can feel. If somebody says, you know, 1 microampere of current, you should almost be able to feel it in your hand. Then microampere, you know, is this microampere? 1 ampere current, how much is it? So first experiment you should do is different levels of current pass through your finger. No, not advised. But say, most of you did high school physics, prepared for these engineering exams, did all kinds of problems in mechanics, physics. Do you know how much is 1 Newton force? If I go around this room and ask you that, go ahead, punch me with 1 Newton force, can you do that? So the gut feel, how much is 1 Newton? Your mom slaps you, and if you say, ouch mom, that is 45 Newtons, then I will say, yeah, you have got it, you know what you are talking, right? But you don't have that. So numbers by themselves don't have much meaning, is all I am trying to tell you. Now if you think of 45 trillion sensors, one way to make sense of that is think of that if each sensor was going to use just 1 watt of power, the whole world will be doomed just with sensors. We don't have that much of power to power these sensors, right? So the first thing you realize that we need to have these sensors which use very little power, otherwise we can't have so many sensors. Okay? Now what is this forecast based on? Look at this, 2007 we had 10 million MEMS sensors in the world, 10 million, 2007. In 2012, barely, in 5 years, this number increased by 1,000-fold. It went into billions of sensors. You know what happened between 2007 and 2012? Huh? Smartphones. Smartphones came, and all of a sudden, the use of these sensors exploded, right? No company, no marketing company in the world had done this forecast that this is going to happen. All the smarty pants of McKinsey's and IIM Ahmedabad's and Harvard Management School, not one person was able to forecast this. Okay? So this is what is called disruptive technology, something that comes in and then just changes the rule of the game completely. So now we know that these mobile devices are becoming so powerful because they have smartness. And what smartness they have? Sensors, right? So that's why the forecast is now we are going to use so many sensors in coming days and months and years that it's going to be full of billions and trillions of sensors. So smart sensors, for example, in health, you will have various kinds of things on you. If you look at you as a person, in your clothing, in your watch, in your specs, in your shoes, you could be loaded. Now when you think of this, somehow you feel an uncomfortable feeling that, hey, look, with so many sensors, is it going to be fun wearing clothes, or is it going to be now a pain? But it seems like that. Now think of this, when somebody first made this shirt, very first time, I am 100% sure that there was no pocket. Somebody thought of, hey, pocket seems like a good utility, you put something, then you can stuff stuff in it, right? And that's how pocket came. Now you are so used to it that you don't think that this is something external. So similarly, when clothing will start coming with sensors built into it, you will feel as comfortable as you feel today. Okay, so no worries. Shoes will still look the same. Inside the sole they will have hundreds of sensors. Why do you care? The sensors are there, right? So it is going to be a reality, and you are not going to feel like you are wired all over the place and you are walking. That's not what is going to happen. So tomorrow you are going to experience things like this, okay? You are going to be wearing clothes, you are going to be wearing shoes full of sensors. This is your smartphone. Look at how, if you open it up and look at what kind of things are inside, you see now there are these red blocks, these are all sensors, right? Sensors. And this wasn't there before. Now it is going to populate, the sensors are going to populate, so many sensors are going to come in there. The forecast is that every person is going to have 1,000 sensors which will be communicating, okay, all the time on them. Okay? That is where we are headed. And these are all heterogeneous sensors, all kinds of sensors. You know, it is not just going to be for motion detection, but you know, you could have electric or magnetic sensors for, you know, leaks, levels detection, force, load, torque, whatever, acoustic sensors, humidity, moisture sensors. So there are applications, are myriad applications. Okay? So I talked about smart devices. What do smart devices do? What do we mean by them? It's capable of making human-like decisions, able to operate autonomously and interactively, and able to respond to changing environment. Roughly speaking, right? You can add things, but this is what we say smartness is all about. So how do you impart smartness? It's mostly about sensing, embedding sensors to things, making them aware of their surroundings, right? This is what we want to do. How do you do that? So what is sensing? Back to basics. What is sensing? Sensing is that you have some stimulus that you want to sense. You have a dabba, you know, some box, some sensor that is supposed to do this. Stimulus comes on it and it gives out a signal that you can record, that you can do something with. That is what sensing is all about. If you open the dabba and look inside, typically what you have is some sort of a structure inside that responds to this stimulus. It must respond to the stimulus in some way. Now if it is a mechanical structure, for example, it could bend, it could deflect, it could vibrate, it could break, it could do various things, right? Now that action or that response is what you want to change, the response you have got. Now you want to change that to a recordable signal. Sometimes you can record the displacement directly, right? If somebody pushes me and I move, your eyes record the displacement directly, right? Therefore, there is a way to record whatever is happening, sometimes directly and sometimes not. So sometimes we use electrical transduction, you know, so displacement has to be somehow converted to electrical signal. How is that done? That is done through transduction. Okay? So this transduction is the key in sensing technology. What is transduction? Let's, okay, before I go there, this is an example. Microphone, I am speaking to you through a microphone. So what is inside the microphone? There is a structure, there is a membrane, there is a basic mechanical element, just a membrane. As the sound pressure falls on it, pressure is coming on the membrane, it deflects, right? So it is deflecting like this because of the pressure. As it deflects, I put another electrode here and this is a conducting surface, okay? Then this becomes a parallel plate capacitor. If it deflects, the distance changes and therefore the capacitance changes and therefore the voltage changes, right? So if I can record that, that is what I have got as a voltage versus time signal, right? So what was acoustic pressure gets now recorded as a voltage. Why do I care about recording it as voltage? Because then I can send it to all the speakers, right? And then the speakers do the reverse, they vibrate bigger membrane so that, you know, with amplification you can hear. So the realization of sensors depends on, you know, this coming together of three things: science, technology and engineering, all three things. Science of transduction, technology to build, how do you make this capacitor so that it will do this job for you, how do you do that? Engineering, because now you have to design that, hey, if I want to record signals in this to this frequency range with this dB to this dB pressure range, then what should be the size of my membrane, what should be the size of the electronic circuit that records it, all of that you have to design. That is what engineering is, right. So let us look at transduction. What is transduction? Transduction, as I said, convert one form of energy to another form of energy. That is what transduction is. So there are lots of materials that do that for you. You know, generally in MEMS technology we use capacitive, piezoelectric, piezoresistive and optical, these kinds of transductions. But you have a host of other transductions: electromagnetic, thermoelectric, piezoelectric, photoelectric, photoelastic. So we need people with expertise in these areas who should know these materials. Most of you are only exposed to one thing out of this whole thing, and that is capacitive. Some of you would have ventured out a little bit and looked at piezoelectric or piezoresistive in some elective, some course, right, but mostly not. But there are so many materials of different kind which convert, it is nature's gift to us, that automatically convert one form of energy to another, right. So unless we know exactly how they do it, and unless we know the relationship, the mathematical relationship between one form of energy to the other form of energy, which is called constitutive relationship, okay, from one set of variables from one energy domain to another set of variables in another energy domain, how does this translation take place? That is called constitutive relationship. For example, in piezoelectric materials that you perhaps know, okay, piezoelectric, where if you press, then there is a charge that develops and you have a voltage developed across the piezoelectric material, across the electrodes. Between stress and voltage, what is the relationship, right? And the reverse, right? If I apply voltage, then actually the material expands or contracts and does mechanical actuation. So what is the relationship between these two? That is called constitutive relationship, okay. That is what you learn through those huge ugly looking matrices, right, but those things are very, very useful, okay, very useful. So that is what you got to know about all these materials, and if you know at least 4 or 5 of them, then you have a choice. If somebody asks you to design a sensor, then you can say, let me think which one is the most appropriate material, which one is the most appropriate transduction mechanism to do this, right, and then you are behaving like what engineers do, okay. Not that you just know one thing and that is it, no, it would not work, right. So this is what transduction is all about. MEMS, so MEMS will require these 3 things: knowledge of materials, because you need transduction, right, fabrication methods, how do you make these tiny sensors, how do you make it. Now you are very, very lucky that you are sitting in this center today. You will see all the facilities, okay, facilities so good that I feel like I want to be in your position today. I want to be undergraduate again, okay, so that we could access these kinds of facilities. These facilities that they are going to have a tour, right, you are going to see, are absolutely world class. All of you, I challenge you, go to any place, any university in the world, any university in the world. You heard that? Any university in the world. If you find a better facility, I will send you there, I will pay for your tuition, okay. That is the kind of facility we have created here, and you will get to see it. There aren't, maximum they are as good as ours, okay. So fabrication and then design, then you have to learn about design. How do we design this, right? Design is specification. This is the performance I want. Performance is given to you in terms of lots of parameters, okay. To target that performance, what must be my geometry, what must be my material, what must be my dimension, right, all of that has to be decided, and how it must be fabricated. Now there are nanomaterials coming, okay, because we work in nanotechnology. These nanomaterials are fascinating because they behave very differently from their bulk counterparts. We still quite do not know how to use these nanomaterials at a length scale which is not nano, okay, but slightly bigger. If you want to make MEMS sensors, then you need materials which will span a few micrometers, right. In micrometer scale, you have already thousands of nano particles, right. So, is their nano character preserved when we go to this scale? This is still a problem, okay. But nanomaterials show incredibly good properties. So, what we are doing is we are engineering materials at nanoscale and trying to see that they preserve that property which they show at nanoscales at slightly longer length scales too, and then use them in these kinds of sensors. You can also build nano sensors, but they are much harder to handle, okay. So, nanomaterials and MEMS and NEMS, these are two things in the intersection. This is an emerging area, okay. How do we use nanomaterials for MEMS? What infrastructure do we need for doing all this kind of work, and do we have it in this country? I am not talking about just this center. National Nano Fabrication Center here, housed in 14,000 square foot clean room. You will see this place, okay, as told. It has photolithography, deposition, etching, packaging, everything that you can think of is there. These pictures are not from the web, okay, that you guys are so fond of. These are all from here. Characterization facility, which has electrical, mechanical, optical, material characterization all under one roof. It's a dream come true, okay. You should see when we have delegations from other universities in the world, all the top shots, when they visit this center, when they go to this facility, their jaws drop. They can't believe that they are seeing this in India, okay, because they do not have this kind of facility. It is a fact. Those machines are there, machines, any top university has all those machines, you know, hundreds of them, but in different places, all over the place. Here, one stop shop, okay. You go to that facility and you can get all of this done in one place. So, IISc has state of the art infrastructure. It is very comprehensive, versatile, flexible, and it is pretty big. It is big because it is designed that way that even for next 15-20 years, we will not have to think about, oh, we are running out of room, you know, let us make another building, none of that. It has been thought through and it has been designed that way, okay. So, we have this facility that you are going to see, you are going to talk to people who work there, you will see all of that. Other national facilities at IIT Bombay, they are our partners in this whole thing. We set up the two facilities together. IIT Madras has a beautiful facility coming up, it is almost there. IIT Delhi, Sri Pilani, upcoming facilities IIT Hyderabad, IIT Kharagpur, IIT Guwahati, commercial facilities Sitar in Bangalore, this used to be ITI Foundry, Semiconductor Complex Limited Chandigarh, BEL in Bangalore. These are commercial facilities that are available. So, it is not that we do not have these facilities now in the country, throughout the country, and we are building more and more, so that all young people like you get opportunities to work in these places. So, let us look at some of the MEMS sensors that we are working on. You know, you have, we work here particularly, we work on gyroscopes, microphones, ultrasound transducers, RF switches, RF components. In inertial sensors, there are two particular sensors which are very important. Both are used in your cell phone, accelerometers and gyroscopes. Both of these devices are required for lots of strategic applications. What does that mean? For defense or for space, right? these areas are such that you are buying it today from outside, and any time any country can say that no, we are not going to give it to you. The moment they feel the threat that hey, you are developing something which might compete with them, then they say no, we won't give it to you. Okay? So they want you to remain there while they are here. Okay? So how do you talk eye to eye, right? Not like this, is by developing your own. Okay? So defense, space, they all want us to develop these sensors here and not depend on outsiders. So we have developed them. For example, this is a gyroscope. If you look at how do you make a gyroscope, you start with your specifications. Gyroscopes are devices that sense rate of rotation. Okay? If a body is rotating in space, what is the angular rate of rotation? That is what they sense. Okay? Now you know that if you are making it for a rocket, then what is the likely rate of rotation that you need to sense? If you are making it for a commercial aircraft, what is the rate of rotation? If it is fighter airplane, what is the rate of rotation? Fighter airplanes, as you know, they go like this and then within a second they will be like this, right? So it is very fast, whereas you do not hope that commercial airlines can do that, right? So commercial airlines, very slow rate of rotation, and therefore the specs differ. Given the spec, you start designing your structure. You design first in some CAD software, right, that you learn, and from there, so this is a design on the design on your computer, then you go make it in a fab like ours. This is fabbed up, and this is an optical image just with a microscope. If you take a scanning electron microscope image, then you can see a bit more details. That here you do not see these comb drives which are visible here. Let me show you little bit more details. So these comb drives are just fingers sticking out of the structure, but these fingers, if you apply voltage across them, then there is an electric field generated here. That electric field attracts this, right, as you are changing the field, and then these combs start moving because of attraction. Okay? So because of attraction they will move in, but then there are mechanical structures attached here, so the mechanical structures get pushed, so there is elastic deformation in them. The moment you switch the electric field, the beams which have been stretched, they want to come back, so they pull it back, and then you apply the voltage again, so it wants to go again and pull it back, so it starts oscillating, right. So oscillations take place, which is the first thing you want, actuation. Look at the comb drives. This is how they look in their full glory. If you zoom in and see, then these fingers are like this. At the bottom there is a cavity, so that they are free to move. Okay? And if you look at how they actually work, this is actuated. So you apply the voltage and then they move, right? Now they do not move so slowly. This is slowed down motion I am showing you. This is supposed to be moving at 7 kilohertz. Okay? So in 1 second it is going 7,000 times, right? So this kind of structures, NEMS, nano electromechanical systems, you have carbon nanotubes stretched as a mechanical beam. Look at here with monolayer of graphene. This is graphene, just a single atomic layer of graphene stretched between two electrodes, right. So you can use that as a membrane or a monolayer of MOS2. These 2D materials, which are new nanomaterials everybody is excited about, you can use them as structures that can be used in sensing. One of our colleagues here, Professor Shankar Selvaraja, he works on optical devices. So he wants to put on a wafer a light source, light coupling, waveguides, wavelength filters, light modulators, photodetectors, all of that he wants to put on a single chip, right. So it is going to have everything that you need for a photonic multiplexer or whatever you want to do with it. Okay. this whole field is called silicon photonics. So if you, any of you who are interested in that kind of area, you can build all of these devices here. We can build them. Okay? So the power that it gives you, with all of this combination on a single chip, you can use that for all kinds of sensing applications, for biology, for healthcare, for chemical sensing, lots of different kinds of things, apart from communication that optical devices are known to do. One of our colleagues works in plasmonics. Plasmonics is an area that you probably don't get exposed to at undergraduate level, right? Sushovan, is there any discussion of plasmonics? I don't think so. Plasmonics, so this is like electron oscillation. Okay, you can make electrons oscillate with photonic energy given to them, and then as they oscillate, they give you back photonic energy that you can use. So how do you make these things work is by having metallic nanoparticles or nanostructures, metallic nanostructures like silver embedded in dielectric composite structures. Okay. So you have here, you can see this is silicon dioxide, silicon dioxide, silicon dioxide. In between you have silver nanoparticles, right? Silver nanostructure. So they have pushed it so far in their construction that you can have silver nanoparticle here. See, this is this is depth wise. What you see is there is a silver nanoparticle sitting here, and there is a silver nanoparticle sitting on top. You want to build these two silver nanoparticles close to each other and have a room, a very tiny gap here, where you can force these electrons to oscillate. Okay? Now that tiny gap, how do you make this tiny gap? How do you make this structure? So they have been able to do, Professor Ambarish Ghosh and his group here, put a graphene layer in between the two and then grow. It's not like you can take silver nanoparticle and another silver nanoparticle and insert this graphene. You can't hold any of them, right? It doesn't work like that. So you have to grow them like that. So you grow a layer of silver nanoparticles, and then you grow graphene on top, and then you grow again silver nanoparticles, and you pray to God that they go and sit on top of each other. The whole chemical process is such that they actually go and sit on top of each other, right? So you build these beautiful structures, and these structures then have this incredible thing that you can make really ultra sensitive photo detector, because they are so close to each other, because you can do this, you can produce these plasmons. Okay? So this kind of thing you can do. Now let's look at something that you all should worry about: agriculture, right? This is mainstay of our economy in India. Okay? Literally our life depends on it. Your life doesn't depend on your cell phone, your life doesn't depend on anything other than food, water and oxygen, right? So agriculture is very important. In agriculture, we use very little sensing right now. This is a wide open area for application of sensing technology. In food production, soil health, seed health, crop health, harvesting condition, all of this right now is done how? Without any sensors. Our sensors, human beings, farmers, they use their intuition about these things. There is no quantification. Storage. When you bring the grain, what is the quality of the grain? When you are storing, is it deteriorating? When you take it out, what is the quality? None of it is monitored right now. When you consume it, nutrient content, what is the nutrient content of the food that you get? You don't know. You hope that it is good, right? Pesticide residues. You all are aware that they have pesticide residues. Your mom washes it, your dad washes it 100 times before giving it to you, with salt and whatnot, because we are scared about the pesticides sitting on fruits, vegetables. Is there a simple way of monitoring it? What if your basin, sink, kitchen sink had these sensors? You put the vegetable, you run the water and it says, you got to wash it 100 times or 30 times, this has a lot of pesticide. That will be a smart sink. What does it take to do that? First wash you do, the water is going through, the tube itself is lined up with sensors, it senses what is the pesticide residue, sends a signal up, there is a MEMS microphone or speaker which says wash it again, right? Done. So that's your smart sink. So this needs to be done. Spoilage, fruit looks very good from outside, right? Inside, mangoes you are familiar with, many a times it's so good, and you open it and it's not so good. So can we sense that from outside itself? I wish that we could do that with human beings too. Crop production, soil health sensors, seed quality sensors, plant health sensors, all of this, in storage, as I told you, for all of this we need sensors. For consumption we need sensors. So we worked on, just pesticides, not pesticide, pest sensors. Pests attack plants, right? Now, when pests attack plants, when they are attacking, they are not calling the farmer through a mobile phone that, hey, I am going to attack your farm, right? So they have attacked. Once they attack, a few leaders come, first they attack and then the whole herd comes and attacks. By the time the farmer realizes that there is attack, it's almost over, then the farmer has only one thing to do, this blanket pesticide all over the place, right? So there is lot of loss. Actually crop loss is incredible, 20 to 40% per year with pest attack. Okay. So what can you do? Can you sense these pests? Now the beauty is that these pests, my God, pests, when they attack, they are emitting something called pheromones, okay, and you can sense these pheromones. These pheromones are specific to specific pests. So if you have a pheromone sensor, then you can sense it, right? So we worked on those, we made a MEMS device, and then on this MEMS device we put, these are just beams, okay, we put a functional surface. So what does that mean? You functionalize it. That means a chemical, a particular chemical, a layer of that chemical you paint on this. You don't take a brush and paint it, you just dip it in the solution and it's done, right? That particular chemical is very, very key element. It only interacts with that particular pheromone, okay, so it's a lock and key, okay, it won't take any other pheromone. So if that happens, then once that pheromone is there in the air, it goes and sits on top of this. We measure the frequency of oscillation before we expose it to the pheromone and after we expose it to the pheromone. So if pheromones have come in, then there is extra mass on it and the frequency drops. So we know with the drop in frequency how much pheromone is present in the air, and therefore you know the extent of pest attack. We also carried out these experiments to see that they are not reacting, this structure is not attracting other pheromones. So we exposed it to other pheromones and we saw that there is no change in frequency when there are other pheromones, but these pheromones for which we have designed it, they are the ones which do that. So this is just an example to show you that, hey, look, you can make these kinds of sensors, okay, but to deploy it in the field there is a long way to go, because right now the frequency of oscillation, that change, is detected with a 1.2 crore equipment sitting in this place. Now you can't put that in the farm, right? So we have to replace that with something smarter. Grain storage, look, this is how grain storage looks right now, okay, beautiful. Actually, it turned out that it is much cleaner than I had thought that these grain storages are. Okay, so we took pictures recently. This is how grain storage is. Do you see any sensors anywhere? No, right? So there is a guy who walks around and sees and goes like this and sees if there is any rot setting in, and that's what your sensing is. Okay? Contrast this storage with this storage. This is your data center. This is full of sensors all over the place. Okay? For hot spots developing inside, cooling fans to go on, off, energy management, blah, 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 everything. Does your life depend on it? No. Does your life depend on this? And yet, look at the contrast, right? So, these storages look so fancy, we spent so much money on them and hardly any sensing done there. So, there is need for it. As I said that if you are going to use so many sensors, where is the energy going to come from? So, you need energy harvesting. You need to pluck energy out of the thin air. How do you do that, right? So, there are things moving, vibrating in nature, right? Look at trees, they are singing all the time, dancing all the time. Why not take energy from them? So, there has to be a way to harvest energy. We have been working on that. You will see if you go to our cafe, there is on the top of this roof, there are these ducts, AC ducts, which are vibrating all the time. From their vibration, we take out energy using piezoelectric materials, and we power Sense logo. If you come in the evening, you will see a Sense logo outside. This one lit up. It is lit up just with that energy, just to show that it can be done. We also have a smoke alarm which is powered by that, and it is sitting in our cafe. You can see these things, right? So, we are working on this so that we can use smaller versions of these. There is an EnviroBat which senses all kinds of gases, CO, CO2, SO2, NO2, O3, temperature, RH, pressure, all of this built into this. Okay? This product has been made here. Now, we use this in this particular hall once to see how CO2 builds up when people are sitting here. We realized that CO2 was building up, and then this structure was modified to bring in fresh air. Okay? So, these things are very useful. Now, we have also done experiments throughout the campus to see where the hot spots for carbon dioxide are, where carbon dioxide builds up. Looking at that, city of Bangalore wants to do it at all cross intersections of roads. Okay? So, this is how you develop sensors. We have developed pressure sensors, which is going to go into LCA. I am running terribly out of time, therefore, I do not have time to do this. Is somebody talking about this pressure sensor? Okay, good. So, you will get to see all of this and how this whole pressure sensor has been developed here. What else lies in future? So, 1 minute and I am done. So, classical gyros, I am just giving an example. Classical gyros used to be big. You might have seen in physics lab if your college was very good or school was very good, several kgs. As a matter of fact, the gyros which were used in ships were several tons. Okay, that is how big these gyros were. So, from there we have come to MEMS gyros, which are a chip sitting on your finger, right? And you feel so smart. You think, wow, look at us, we are so smart. And then you start looking at nature, and nature says, really? So, here, look at this. It is an insect, okay? It is an insect. It is a fly, soldier fly. It has huge wings that I am not even showing because it is so big. To show you a tiny instrument it has here called Haltier, okay? So, the wings are ahead, only you see this part of the wing just slight part of the wing you are seeing. Okay? So this is because this total length is about 800 microns here, okay, from here to here, less than a millimeter, and a blob like structure. So if you look at it, it looks like this. This is a gyroscope that the fly uses. Okay? So beautiful, so elegant. One of my students has spent 6 years of her life figuring out how does this work. Okay? And this is biological structure. So, you can't ask the fly that what happens when you do this, so you have to figure all of this out, and for such a tiny structure, how do you see what the dimensions are inside, what material, what kind of material, what kind of structure. She did tons of work. And when we figured it out, I felt like giving up. That look at nature's design, so elegant, so beautiful, so small, so smart, and compared to that our designs suck. But that's what we are looking at, and that's where we have to go. So this is the fly. Look, this is flying on the top of a needle. Sorry about that. Apologize to the fly. And here is the haltear going up and down. You see that? This tiny white structure. Okay. So this is the haltear, and at the base of it, it has strain sensors. Okay. At the base of it, it has something called campaniform sensilla, which is strain gauge for the fly. So if you get interested, you can read our papers. It's a fascinating mechanism how the fly uses this as a haltear. Now get this. This is the smallest insect in the world known. 200 microns length. 200 microns. That's it. All sensors are inside. It's a packaged system. Okay? All sensors, actuators, everything. So this is the future of MEMS. This is what we are looking at. This is where we have to go. Okay? From where we are. We make these tiny structures and we put electronics and still becomes this big. Okay? If you look inside your cell phone, the reason that they are so big is because they still require these big structures. But look at this thing, right? And this hair-like structure at the end of the wings. It's like a limit of photolithography, that Dr. Gopal Hegde is expert on. It's a micron gap there. Okay, beautifully made structure. What do they use it for? They use it for actually sensing. These insects are parasitoids. They lay their eggs inside the eggs of other insects. Very smart, because they don't want to spend money on infrastructure. Okay, energy on infrastructure. They want to use somebody else's infrastructure and get their work done. So these eggs are so small. Those insects which lay eggs, they lay eggs in the pores of leaves inside there, and then these guys are going and filling those pores, and inside they feel the egg and the temperature. Is it good enough for me to lay eggs inside? All of this sensing is taking place at that scale with the sensor. How do these sensors work? Open question. If you want to do PhD, most welcome. Thank you very much. Sorry about exceeding the time. I forgot how many slides I had. Okay. Any questions? Yeah. Good question. Why don't we make 3D sensors? These are 2D. So the technology that right now we use is such, right, that only planar structures we can make. Everybody is working on 3D structures. Okay? As a matter of fact, we have figured out that even if we don't make 3D structures, we can make 3D systems. Even that we don't do. Right? So here is one of my colleagues, Dr. Prasenjit Sen, who is working on this, that why don't we work on 3D packaging, so that we have some sensors, health monitoring sensors here, drug delivery, energy storage here, inertial sensors here, CMOS stack here, You know, so can we do this? Even doing this is extremely hard, because thermal management inside. You are looking at, you know, this looks pretty big, right? Air can flow easily here, but when you are actually looking at this device, this is very small, right? So the thermal management, you know, the electrical energy dissipation, also just ESD issues, okay, in these devices, all of that has to be worked out. It's not a simple thing that you can just stack them, okay. So there is a lot of research right now on this issue. How do we do 3D stacking? Yes, sir. Any other question? Quick? No? Good. Very good. Thank you very much.
During lunchtime or even tea break if he is around. So with this I thank Sir RP, and on behalf of IEEE Nanotechnology Chapter Bangalore, my pleasure to hand over this small moment.
Thank you, sir.
Thank you, sir.
Sushobhan is next, is it? Yeah, I'm sure that he didn't come to listen to my lecture.
Next topic is by Sushobhan Avasthi. This is from Center. Yeah. Okay. Can you switch on this light? ಈ ಲೈಟ್ ಹಾಕ ಒಂದು ಕಾಣೋದಿಲ್ಲ. Yeah. Let me introduce Dr. Sushobhan Avasthi. Dr. Avasthi has completed his PhD from Princeton University and his BTech from IIT Kanpur. His group's primary focus is on solar cells. He's expert in solar cells. They work on novel material systems like metal oxide, perovskites, and organic semiconductors with traditional absorbers like silicon to form low-cost, high-efficiency solar cells. He is also interested in large area thin film transistors which are used in displays and large area sensors. Professor Sushobhan, I think he's ready.
Yes.
You can take okay.
All right. Hello, everyone. I'm assuming the sound is mostly under there. Here's how we. You want this? Okay. Yes, we're recording. Am I audible, or am I too loud? People in the back. Okay, I'm good. All right. So my name is Sushobhan. I work on solar cells. What this talk is going to be on semiconductor fabrication processes. Okay. So this is supposed to be a slightly generalist talk. I'll try to introduce you to the main components of what a typical fabrication process to make the devices that RP showed you needs to be. I'll not go into any details. If you are interested in the details, I think we are going to talk more about lithography later, and we are going to talk about packaging, etc. later. So you will get a deeper insight. You'll get a deeper insight into each of these individual components. What I'll try to do is say general and give you a general overview. If you have any questions, please stop me along the way. I'm happy to answer any questions. Let's try to make it an interactive session instead of a boring session where half of you fall asleep. All right. By the way, there's an interesting story. So RP talked about that we measured carbon dioxide in this room. Do you know why we did that? Because RP started sleeping, and he's like, it can't be that all the talks are boring. There must be something wrong in the room. And we figured out the carbon dioxide levels in this room were rising. So we fixed the air conditioning. So anyways, the point is, there's no reason to sleep in the lecture. Let's wake up and let's be interactive. Ask me questions. Okay? All right. Okay. So basically, an integrated process means fabricating a certain pattern on a silicon wafer. I have arbitrarily broken down this process into 4 bits. So first you select a wafer or a substrate to make your material on, right? It could be silicon, it could be gallium arsenide, it could be glass, depends on your application. Once you've decided your wafer, you've decided your application, you look at what material you need, what quality of material do you need, and after that you have to typically deposit something on it. A single material is usually not enough to get enough usage out of. Like a single material hunk of silicon is not good enough, a single hunk of gallium arsenide is good enough. You typically need to deposit other materials on it, make structures on it, and that is what I would call an additive process. The two things that I would discuss in this lecture are a chemical method of depositing things and a physical method of depositing things. Once you have deposited something on top, in this case is silicon dioxide, end of the day that is also not enough, because if you have a hunk of silicon and a hunk of silicon dioxide, that's just a blanket layer. That's not good enough. If you want to make the structures that RP showed you, you saw those 2D images, right, with the comb drives, etc. So you have to etch some sort of pattern on top of that wafer. How do you etch that pattern? It's through lithography. We'll look into the details a little bit. After you have etched a pattern, that pattern itself is also not enough. You have to, in general, etch grooves. So again, look at the comb drives that RP showed you, right? There were deep ridges in the material. How do you create those deep ridges? So you actually do some sort of etching process to remove the material. So there are, in some sense, these 4 processes. So there has to be some addition, there has to be some subtraction, and where do you do the addition and subtraction? That is decided by the lithography, by the pattern that you make on top of the wafer. This will make a little more sense a few slides down the line. So first, substrate selection. Typically, so in electrical engineering or in semiconductor, people talk about wafer. So what is a wafer? Wafer is basically a substrate. It usually is circular, but it can also be rectangular, on which you actually do the microfabrication, you actually make the device. It's usually around 200 to 2000 micron thick. So 2000 micron is 2 mm, 200 micron is twice the width of a human hair. Okay? And thickness is usually decided from materials by mechanical considerations. End of the day, you want to be able to handle it, like you see in this picture. And in order to be able to handle it, it cannot be thinner than a certain level. Though the device requires only a few tens of 20 micron maximum, for just mechanical consideration, the actual wafer is a little thicker. It typically is square or circular, and it's usually polished to a mirror shine. Can you guys guess why? Why would you polish a wafer before using it? Partly contamination. What else? Reliability. So end of the day, you're making patterns on it. It's harder to make a pattern on a rough surface. It's easier to make a pattern on a smooth surface. And that too on micron scale, right? If you have a crease on a micron scale, what do you do? If you have a ridge on a micron scale, what do you do? Then what materials are available? So frankly, any material which can be called a semiconductor can be used for fabrication. Typically, these tend to be group 4s. Everybody remembers the periodic table? So this is a subset of the periodic table. So if you look at the group that carbon belongs to, so that's the group 4 of the periodic table. So it has carbon, silicon, germanium. Silicon and germanium, in fact, silicon on its own is by far the most important semiconductor we have. But there are other materials that come out. For example, instead of just using group 4, you can select one from group 3 and one from group 5. On an average, you have the same number of same number of valencies, but it's what is called a 3-5 compound. You can do the same thing with saying 2-6 compound. So there's a lot of semiconductor variation just because you can keep making these compound semiconductors with more and more complexity. So that's the 3-5 semiconductor like gallium arsenide, which is very popular, but things like gallium nitride are coming up. Recently, there are these LED bulbs. What do you think LED bulbs are made of? What semiconductor? No? Gallium nitride. It's not gallium arsenide. So these semiconductors are coming up purely for these type of applications. And as I said, group 2, 6, etc. But this is just the start. If you really are interested in some very niche applications, I just got this screenshot from a website. If you can't read everything, that is okay. What I'm trying to highlight is there's a bewildering variety of semiconductors that today you can buy. Depends on their application. Some of them are piezoelectric materials, some of them are ferroelectric materials, some of them are useful for radiation detection, etc., etc. As a scientist, thankfully, so many of them are so expensive that you never get to use them. And in reality, you default to a few practical semiconductors that you use. So one of them is just silicon, the well-known workhorse. Germanium. Which was the material of the first semiconductor device was made on? It was germanium. Even though silicon has superseded it in popularity, the first semiconductor was actually on germanium. Silicon, germanium, which is just an alloy of the two, silicon carbide, gallium arsenide. In terms of sometimes you require insulators for certain devices, and for that case you can use sapphire, quartz, glass, and plastics. Okay. Typically, when you go and buy a silicon wafer, you have to give a whole bunch of specifications. The aim of this slide is to tell you what those specifications are, at least in some amount of detail. And the other thing is to highlight what are the important points you need to think about when you say design a wafer. So one of the things is, what size do you want to buy? So the first question to you is, why do you think we have multiple sizes? I mean, that's a simple answer. Huh? You would think it's application, and frankly, it's just history. What happened was making single crystals of these things. So these are perfect crystals. It's very hard. So in 1960s, we could only know how to do this on the 1 or 2 inch scale. Over a period of time, we have gotten better and better at making these things, and today we can make these things in 4-inch perfect single crystal. So you have to understand, this is a very hard problem. You have seen crystals of sugar, right? Have you ever seen a single crystal of sugar that is 14 inches big? It is a hard problem. It's not easy. It has taken a lot of work and effort to actually increase the size. And what does increasing size buy you? Why the effort? The number of devices you can make in one go. So silicon chip, if you have ever seen it, is actually this big. The more number of chips you can make while processing one wafer, more the number of devices you are making, the cheaper you are making them. So if there's only 1-inch substrate, then Intel can only make 2 chips at a time. If there's a 14-inch substrate, Intel can make 1,000 chips at a time. And that is the advantage. That is why semiconductor becomes more powerful and cheaper every year. Then orientation. This is because it's a single crystal. Each crystal has orientation. Different crystals have different properties, so you have to select which orientation you need. Grade. When you make these single crystals, it does not come out one uniform quality. As in reality, like things come in different qualities. So you have to, based on your application and your cost, select what type of material you want to take. If you are making a MEMS sensor, you don't care about the electrical properties. So you're happy with a mechanical grade wafer. But if Intel is making top of the line semiconductor chips, it matters a lot to them what is the electrical quality, so they will only make it on a prime grade wafer. But it will be substantially more expensive. Okay. Then which method you know? Let's not talk about this for now. Thickness, we have already discussed this. Resistivity. This is the how much dopants you have in the system. How many of you here understand doping? Who does not understand doping? Because I have a lecture on a slide on it, and we'll discuss it at that point. Everybody understands doping. I don't believe you. All right. Finish. Sometimes you want single-sided polish. Sometimes you want double-side polish. Double-side polish and single-side polish ultimately comes down to application. For some optical, for example, applications, you would like double-sided polish wafers. If you have devices on both sides, you may want double-side polish wafers. So those are the things you have to tell your guy who gives you wafers before you can proceed. And based on your applications, you have to make a judgment call on which material you require. The next step, cleaning. Yeah. It depends upon what orientation. So these orientations are subject to the crystal. So silicon is an FCC, tetrahedral lattice. So these are the facets that are available to you. In some other cases, you could, for example, in zinc oxide, you could have a completely different facet. End of the day, it boils down to application and the ease of making that facet. In order to grow a crystal of a reasonable size, can you even access that facet? Some of the facets that you mentioned may not be possible in a crystal. So it depends on the application. This is for silicon. It could change for other materials. So cleaning. This is one of the things that is one of the most important aspects and also one of the most underappreciated aspects. The brilliance of semiconductor technology is not the fact that we can make these devices. The brilliance is we can make them as reliably as we do, and we make them of as high quality as you do. In terms of how clean or how perfect a certain system is, material science cannot give you tests that can measure things as precisely as an electrical circuit can. Things that are not visible on a materials test matters when you make device. So the perfect test of a material quality is actually not doing a materials test, it's actually making a device out of it. That is how far device making technology has gone. Okay? Am I making sense? Like, you cannot test the quality of a material using today's test, even today, with as fine a precision as you can if you make a device out of it. The device is the most sensitive measure of material quality. And that in great deal has to do with how well we clean these things. Okay? So first thing, why is cleaning important? And then I'll just very quickly discuss 4 of the cleans that have been developed that are commonly used in silicon technology at least. So chemical contamination ruins things. When you're making things on nanometer scale, a nanometer dust particle is a problem. Okay? The size of today's Intel devices is 11 nanometers. Okay, 14 nanometers, sorry. They're going to go to 11 nanometers. At that level, you cannot have a random dust particle setting because it's not just a matter of one device. Intel is using 1 billion devices. 1 billion devices need to work perfectly for making one Intel chip work. If even one of these devices fails or 2 of those devices fail, the circuit doesn't work. So they have to actually ensure things are clean on a nanometer scale even when you are making it on 14-inch substrates. That's a very hard thing to do. There's also a question of reliability. Well, things may work when they first come out of the foundry, but because of one dust particle embedded in the silicon dioxide, over a period of time, that device will fail faster than you expect it to. Today, everything from medical devices to airplanes are run on electronics. They run so because the electronics is so much more reliable. And that reliability comes because we are very, very careful with how we make them. Then it's also a question of controllability. To appreciate this, you are making you have designed a certain process to make a certain structure. You want to do it day in, day out, 365 days, 7 days a week. So that is process to process. Let's call it non-variability of the process. To run, variability needs to be very small. Because if that variability is large, then every day somebody has to tune your process. And if you have to tune your process every day, then again, that is not a viable way of making devices. And end of the day, the problem of cleaning or the importance of cleaning, especially in a lab like ours, is it does not just affect your work, it affects mine. There are common instruments that are used to manufacture several things. If you do something that messes up a device, you don't just mess up your device, you also mess up mine because I come after you and I use the same equipment to make the same device, and 1.5 crore machine is bad or down because you messed up. So there's a social aspect to it, a social responsibility aspect to it. Okay. So what are the sources of contamination? Humans. Wherever we go, we contaminate. So our organic residue from resist. So these are, so some of them come from you. In fact, most of them come from you. A clean room is a very clean environment as long as humans don't enter it, but we need to enter it. You shed skin. You may not know how much, but you do continuously. You shed hair continuously. The number of times I have shouted at students who have like flowing hair in the clean room. In an actual commercial clean room, you're not allowed to use face creams, you're not allowed to use oil, you're not allowed to cut your nails the day before entering the clean room. It is a very strict environment, and that is because of how sensitive the whole process is. If you ever touch a wafer with your bare hand, that wafer cannot be cleaned. Never, ever. Throw it away. Please don't bring it to my clean room. You cannot clean sweat, you cannot clean organic residue from a wafer touched by a human. It has to be handled using dedicated tweezers, with gloves, with complete. Have you seen that Intel ad where people are wearing bunny suits? There's a reason they wear those bunny suits. It's required. All right? So that's the contamination. This is just to highlight to you what is the state of the art. So ITRS is basically the group of semiconductor manufacturers. So they give out specifications to how clean something needs to be. They give out specifications for equipment, etc. So this is the specification for contamination. This is 2015. This is the goal in 2024. So killer defect density. This is the density of a defect that will kill us one device, not the whole chip, one device. They want it to be less number per centimeter square. They want it 0.0033. Okay? Let me go down further, which will actually highlight critical surface metal contamination. This is number of atoms per centimeter square. We want it to be 10 to the power 10. This sounds like a large number, but how many atoms do you think there are per centimeter square? The answer is on the film. Number of silicon atoms on the surface is 10 power 14. Basically 10 power 15 if you round up. So there are 10 power 15 atoms of silicon on the surface. What is the metal contamination you are allowed? 10 power 10. In terms of how pure is that? 99.999% pure. Day in, day out. That is a very high level of purity to exist in a manufacturing environment. Semiconductor industry by far is the only one that can actually pull it off. No other chemistry, no steel, no other industry can ever promise you 99.999% purity every time. Okay, so that's the importance. Okay, so what do you use? You use deionized water. Basically, it's water which does not have any ions, it does not have any metal contamination, it does not have other materials that you do not want on the surface. It is better than distilled water. Distilled water is not pure enough for semiconductor industry. And if you do semiconductor process, you only use DI water, even if the paper doesn't say so, because the paper assumes you're using deionized water. You also use something special grade of chemicals, which are called CMOS grade of chemicals. These are the cleanest grade available on the market. They're cleaner than what chemists call pure or chemists call clean grade. Okay? And these have typically impurities less than 10 or 20 parts per billion. Okay. Cleans. So there's few cleans that have been developed to clean the silicon surface before you start your process. So one of the things is called the Piranha clean. It actually is sulfuric acid peroxide in some ratio. Okay, and you typically take your wafers, dip it in this solution. It's a very aggressive solution for something at around 120 to 800 degrees for 15 minutes, and that's designed to clean a lot of organic and other type of junk that accumulates on top of a wafer. Okay. The mechanism is actually that H2SO4, boiling H2SO4, is actually a oxidation reagent. So all the carbon-based organic contamination that is on your wafer, H2SO will convert it into carbon dioxide, and that radically cleans your top of the surface. Then there is, for really, really specific or really very special things, for example, during the great oxide growth, people do something called an RCA clean. It was developed in 1960s in US by a company called RCA. RCA was a company that used to make TVs. It doesn't exist anymore, but they developed this process. And what they basically do is they have 3 steps, an SC1, an SC2, and SC3. Step 1 actually cleans organic contamination, step 2 cleans metal contamination, and the step 3 cleans the oxide that forms. I'm not going into detail. I think these details are not terribly important. End of the day, these cleans are used to get to ppb levels of contamination on the surface. After that, you are ready for additive processing. And this is the meat of the talk. Here we are going to discuss 4 things. There are a lot of ways of depositing things on a semiconductor. I have just taken these 4 as an example. So one is diffusion. Diffusion is one process through which you introduce dopants into the wafer. We will discuss what dopants are in a minute. Then there is some things, then there is there are a couple of ways in which you can deposit other materials on top. For example, one thing, you can grow things using silicon itself. So you have a silicon wafer, and you can provide it with oxygen, and silicon oxide will grow on its own. So that's what I mean by native growth. You're not adding any other material, it's growing on its own. You can also add material that is completely alien to the silicon surface. For example, you can deposit silicon of a quality of material different than what is on the wafer. So you can deposit fresh layer of silicon on top of already existing silicon. So that's through chemical vapor deposition. And the third is, supposing you want to deposit metal on silicon, say for making electrodes. And that's the third or fourth example process. So these are the 4 types of depositions that are typically done on top of a silicon wafer. So what is doping? It's adding a specified impurity. It's not just adding any impurity. It's adding a specified impurity. And the specificity comes from valencies, or one way of explaining it through valencies. So here's your silicon lattice. How many valencies? 4. So if you substitute one of the silicon with something from group 5. So remember, this was group 4. How many valencies does group 5 material have? Group 5. 5 valencies. So it sits in a silicon lattice where 4 of the valencies are satisfied, 1 isn't. So that's the extra electron. And so that extra electrons basically increases the conductivity of the material, and you call it material n-type doped. Okay? So this is what I'm trying to do, that there are extra electrons in the conduction band of the material. If you don't understand valence conduction band, that's okay. So but you have an extra electron in the system. This is called n-type. you can add something from group 3. How many valencies does group 3 have? 3. So here it wants to attach to 4 valencies, but it can only accommodate 3. So then there is one extra, it's basically a lack of electron, or in semiconductor parlance, there's a hole, HOLE, and that hole can also move in the semiconductor. So you can think of electron as a negatively charged particle in a semiconductor, the hole as a positively charged particle. So these are required to basically make electrical structures inside a silicon. So you take a hunk of silicon, but you make some parts p-type, some part n-type, and then you have a electrical circuit on top of the silicon. Now, how do you actually introduce these dopants into the silicon? So what you use is the process of diffusion. So diffusion is a relatively simple process, right? That I light an incense stick at the other end, and I smell something. Why? Because the molecules of that are coming from the incense are drifting through the air because of a difference in gradient, and are getting to my nose, right? Now, if you take a hunk of solid, say this, and I put some ink on it, will it diffuse in? Why? Because this is solid. But if I increase the temperature, then molecules of this solid start moving. And because of the molecules they start moving, they actually make voids. And in those voids, these materials can actually get in. So the diffusion is a process that starts actually happening even in solids. So it happens at room temperature in gaseous medium, but even in solids, it starts happening if you raise the temperature high enough. So that's what they do. They put a wafer in a furnace at 800,000 degrees C, and then they introduce the dopant atoms. And those dopant atoms, just by diffusion, statistical diffusion, kind of start entering it from the top. And then you create a profile inside your semiconductor. And that profile looks something like this. You can get different types of profiles. All profiles start from some number. So this is a normalized number, so it starts from 1, and it falls down as you go deeper into the bulk. That makes sense? At the surface, it will be highest concentration, lower concentration underneath. So it's always a decrease in concentration. And by by either giving it infinite amount of dopants or giving it a finite dose of dopants, you can get different types of profiles. And which type of profile you need, you have to look at your application. What sort of dopants and for different types of dopants, you need different type of dopant sources, right? So for boron, you will introduce different types of materials. For phosphorus, you will different types. So the dopant sources can either be solid. You can introduce, say, in a small crucible, you can keep some boron oxide inside the wafer, inside the furnace. So that the boron oxide will evaporate and diffuse in. You can do the same thing with a liquid source. You can keep an ampule of liquid, right? Or you can also do it with a gas by introducing a gas containing boron. And for different dopants, you can actually have solid, liquid, gas source, and this is just a list. What I want to also highlight is boron is a p-type dopant. Phosphorus, arsenic, antimony are all n-type dopants. So which would you select? The answer is it depends on application. Each of these has a different size. And different size means compared to silicon, it fits into the lattice either happily or unhappily. So if it is the same size as silicon, which is say arsenic, the misfit factor is 0, meaning it's roughly the same size as silicon. But phosphorus is much smaller and antimony is much larger. So they are unhappy in the silicon lattice. Because they are unhappy in the silicon lattice, they either diffuse too much or they don't diffuse at all. And those actually decide how deep the diffuse changes, how fast the diffuse changes, etc. And those properties decide the application. So both of them, all of them are n-type materials. All of them will give you extra electrons, but the depth of diffusion, the diffusion profile, etc. will change. Next deposition method that I'm going to talk about is native growth. Native growth means that you are growing a material, but you are not adding extra elements. So for example, when you're doing boron doping, you are adding boron, right? Here, you are just keeping
We'll have a 10-minute tea break. We're running a little bit late. And just one more thing, we are taking the consent of the, the speaker and recording all this, and we will be sending it through mail after the event. I just saw many people taking photos, so please don't worry. We will be sending the videos if the speaker gives us the consent. Okay, yeah, we'll break for tea now.
this.
Yes, welcome back to the second session of the morning. Uh, this talk is by Professor Digbujoy Nath. The title of the talk is Materials to Device Characterization of Compound Semiconductor Transistors. I think you have been hearing so far silicon, okay? A single semiconductor is a compound semiconductor now. So let me introduce Dr. Digbujoy Nath. Dr. Digbujoy Nath did his PhD from Ohio State University and his engineering from BITS Pilani. His research areas include GaN-based electronics, 2D materials, novel materials and devices, and transport in semiconductors. His group will explore unconventional and novel transistors such as hot electron devices, tunnel diodes, etc. to overcome this limitation. They are also interested in exploring novel optoelectronics and electronic devices based on hybrid 2D, 3D materials by combining MX2 type materials with GaN, gallium nitride, to take advantage of both material systems. Let's welcome Digbujoy Nath. We can start.
But I think I'm audible, right? So I'm audible, right?
No, sir.
I'm audible. Right. Okay, so I'm a non-silicon guy, okay? So just now you have heard so much talk on silicon. Non-silicon guys don't try to compete with silicon. They don't try to overtake silicon. They don't try to replace silicon. They try to complement silicon. Okay? All right. All right. So I think I'm a little bit better now. All right. So silicon is the king. It will be a king for a really long time, I think. The non-silicon people like us, we try to complement in the areas where silicon cannot deliver, right? There are certain areas silicon cannot do. And the idea is to help silicon get those either in electronics or optoelectronics, right? For example, I will assume for my talk that you have some background on semiconductor, very basic. For example, you know what is a band gap of a semiconductor, what is lattice constant. Lattice constant is the spacing between atoms, okay? And you know what is direct and indirect semiconductor. That three assumptions I will make. For example, silicon cannot emit light, you know that, right? So we do not have silicon laser and silicon LED, right? So if you want to have all these LED lightings and laser diodes and many other displays and all, silicon cannot work there. So compound semiconductors are non-silicon. They are of different materials families, and they enable us to get things done which otherwise would not have been possible, okay? So broadly speaking, I will try to go on the topic why we need compound semiconductor, right? There has to be some motivation, as I already told you. And how do we get them, you know, deposition, or which is called growth. Like silicon, you know, just now Sushovan Avasthi had already explained to you probably like how silicon is grown, Czochralski method and other kind of things. But gallium arsenide or gallium nitride kind of things are not grown like that. They are grown in a little different way, actually substantially different way, okay? And primarily then I'll focus on how to characterize these materials and how to characterize the devices that you made, primarily transistors, okay? HEMTs, high electron mobility transistors, all right? So
human civilization has been defined by the material. Okay, so Stone Age, Bronze Age, Iron Age, and then we had the Silicon Age, right? So this was told to me by one of my friends actually many years back. He said that it is the material that defines human civilization most importantly, right? So right now we are in the Silicon Age, and beyond, what do we see looking beyond? Silicon will still continue, as I told you, but let's see what are the areas where silicon fails, or you need other kind of materials, for example. Okay, so this is the periodic table. I mean, a part of the periodic table that shows you the primary compound semiconductor materials that are used for transistors. Okay, essentially you take group 3 and you look at aluminum, gallium, indium. Okay, and then you look at, say, phosphorus and arsenic in group 5. Now these 5 elements, if you mix and match, okay, if you have all kinds of permutation combination, then you get the conventional 3-5 semiconductor family. For example, you have aluminum arsenide, aluminum phosphide, or gallium phosphide, gallium arsenide, indium phosphide, etc. Right? You can also mix them in forms of alloy. For example, aluminum, gallium, arsenide. Okay, so some of the components will be aluminum, some will be gallium, and then there will be group 5 arsenic. Right? So you can do a lot of permutation combination, and you get what is called the compound semiconductor family. Okay. Here there is also another family called the nitride family. So if you take the nitrogen, for example, and you mix and match with aluminum, gallium, indium, then you get aluminum nitride, gallium nitride, indium nitride. Right? These are compound semiconductor. You can also have alloy, for example, gallium, indium nitride. Right? So in a nutshell, these basically consists the compound semiconductor family for transistors. There are other elements like antimony, bismuth, and other things. They are not as much used for making the transistors. Right? They have other applications in some other areas, but gallium arsenide or gallium phosphide and gallium nitride based devices for the last 20 years or so have been transforming our technological landscape to a significant extent. Okay, so the advantage of using this different kind of compounds is that you can tune the material property. For example, silicon has a band gap of 1.1 eV. It's very difficult to change the band gap of silicon when it is silicon, right? So you mix with, say, germanium, for example, you get silicon germanium alloy. You try to make little bit changes, but the window is not so large, it's very narrow, right? You know what is a band gap, right? So if you change the band gap, the light that you emit or absorb also will change according to band gap, and many other parameters can be tuned. So these materials, because you have a wider zoo of window, like, so you have a lot of things that you can do with this. For example, this is band gap on the y-axis, okay? And here on the x-axis I am showing you what is the fraction of gallium arsenide and aluminum arsenide in an alloy, say aluminum gallium arsenide. Okay, so you see that if you go from gallium arsenide to aluminum arsenide by changing the aluminum composition, say at 50 you have 50% gallium and 50% aluminum, so it's aluminum gallium arsenide 50-50, right? So your band gap actually keeps changing, right? Your band gap also can be tuned from direct to indirect, for example, and the band gap keeps changing. If the band gap keeps changing, then for example in optoelectronics, the light that you can absorb or emit also keeps changing. A lot of material parameter, effective mass, dielectric constant, they all keep changing, right? So you can do something called engineering the energy landscape or engineering the energy band diagram, okay? That allows you to make different kind of LEDs, lasers, transistors, etc., right? So so this kind of flexibility is very easy to achieve in the compound semiconductor and not in silicon, right? And silicon always stays indirect, for example, right? So and when you change the band gap, the material is changing, right? So one of the most important characteristic of material is the spacing between the atoms, which is called the lattice constant or lattice spacing, right? So for example, here on the x-axis I am showing you the lattice constant in nanometer, say 0.3, 0.35, etc. nanometer. That is the spacing between the atoms. And on the y-axis you have the band gap. Okay. So for example, if there are too many materials here, we don't have to consider all of these here, but primarily say gallium phosphide, gallium arsenide, indium arsenide are here, for example, and silicon is here over, right? Silicon has a band gap here, and then the lattice constant is here, right? And this is the gallium nitride family I was talking about. You see gallium nitride, aluminum nitride, indium nitride, this band gap range is huge, right? It goes from almost 0.7 eV, which is near infrared, to almost 6 eV, which is deep ultraviolet. This is the visible spectrum. So the visible spectrum roughly encompasses between 2 eV to 3.2 eV, for example. So, and this is infrared here, and this is ultraviolet here, right? So gallium phosphide, gallium arsenide, and all these kind of materials, conventional, they go to like say red, yellow, and then the infrared range. So all kinds of mid-infrared or even near infrared, I would say, kind of detectors are based on this kind of materials, right? and gallium nitride family can encompass the entire thing, but primarily it is used to make violet, blue, kind of LED. And not this year, but last year's Nobel Prize in Physics went to Shuji Nakamura and 2 of his colleagues for actually inventing or pioneering the LED, right, the blue LED, which enabled the white LED, right. The blue LED actually leads to white LED, and that has changed the energy landscape of the world, right. There's a huge, it's very efficient, it has a very long lifetime, and then you have a lot of advantages of using LED, although it's a little expensive, so they're trying to cut down the cost, but it has much more benefits, many more benefits than conventional fluorescent or tube light also, right. So gallium nitride is the material on which Shuji Nakamura and other Nobel laureates had worked, right, and it enables violet and blue LED basically, right, that's on the optoelectronic side. Okay. So, so these are the things in the optoelectronic front, for example, that silicon cannot do, and we are people are actually using this kind of materials to make a wide range of detectors and LEDs, etc. This is also the same figure in a way, but it's more zoomed to show you the conventional 3-5 semiconductor, gallium phosphide, gallium arsenide, indium phosphide, right. So they also encompass the red, yellow, amber, orange kind of spectrum, right. But the the beauty of this system is that most of their materials, they have similar lattice constants. So if you look at the x-axis, the lattice constant of many, for example, over here, these shaded lines show the how you travel if you move from one compound to another compound, for example. Okay, so if you want to go from say gallium phosphide to gallium indium phosphide, you have to go along this line and then come down here. So lattice matching becomes easier here. What is lattice matching? Lattice matching is that, so okay, for all these different materials to make LEDs and detectors and transistors, etc., you need different layers of these materials on top of each other, okay, to enable the function. So you cannot just deposit, I'll come to that later, you cannot just deposit 2 different materials on top of each other. They have to have similar arrangement of the atoms, right. You cannot put, for example, gallium phosphide on top of wood, right. I mean, you can put it like that, but it will not have a bonding. To enable the vertical bonding and to have a crystal structure, you need to have a similar atomic arrangement. For that, you need to have a very similar lattice constant in the both on the platform on which you are growing, which is called substrate, and the layers that you are growing, right. So in gallium nitride system, that has been a problem. The spacing between the lattice is pretty different, and so this material system is not as good in material quality as this system. This is more mature, okay. So gallium arsenide has been around since 1980s, for example, and gallium nitride has been around since 1995 or so, okay. And both these things developed only because certain techniques were invented in late 60s or 70s and were mostly matured in 80s, which are called epitaxial techniques. That means the technique to grow these thin layers by atomic layer precision, one layer over the other, that enabled a lot of Nobel Prizes actually back in 1980s, quantum Hall effect, fractional Hall effect, etc. They could be discovered only when the techniques were invented by people to grow these materials at a very precision level, okay. Alright, so I told you that silicon cannot do everything. So this is a schematic and a kind of a cartoon that shows power or voltage on the y-axis and frequency on the x-axis. So you see silicon is a very dominant chunk of this for say low power, low voltage, even to some extent high power, high voltage. But if he has to go very high speed, this is frequency, gigahertz, terahertz, right? If he has to go very high speed or if he has to go very high power, then silicon does not perform as well as say gallium nitride, okay, in terms of switching efficiency, heat loss, etc. So gallium nitride is, for example, the promising and the ideal candidate for actually one of the ideal candidates for extending the performance of transistors or electronics beyond the conventional voltage and power frequency range, okay. And for example, if you want to go very high, say near terahertz, exactly, few hundred gigahertz, for example, then indium phosphide or gallium arsenide based transistors are what is actually preferred. They do not give very high performance in high power, but for low power, high speed applications, there is always the need for this kind of materials, okay. So if I look at gallium nitride, for example, okay, so the broad areas of gallium nitride transistors, which we may not be completely aware of at the ground level, but they are actually, there's a huge market, there's a huge industry and huge effort for the last 20 years is in high speed RF and also in high power switching application. So let me go here. So in the mobile base stations, you need these kind of RF amplifiers to process signal, receive and transmit, and you need a lot of power handling capability, right. So back in 1990s, gallium arsenide was being used there, but then gallium nitride was first demonstrated in 1995, and it could demonstrate up to 10 to 20 times higher power at the same frequency. So they have been currently used in enabling this the amplifiers in mobile base stations, in satellite communications already NASA and European Space Agency have been putting up gallium nitride transistors in space. Why? Because they are much smaller in size and they can deliver and handle much power with much more efficiency, right? The device footprint decreases. They also can handle much more temperature, right? Up to 500, 600 or even 1000 degrees Celsius, the transistors will still work, but silicon will not work, for example, right? So all these kind of RF applications and high power level are being now, gallium nitride is being currently used in those. Power switching and high power at low frequency, of course, is another area that is going to be really, really important. The petrol and gas that we have in the earth is being depleted. It's like a few billion barrels of petrol is depleted every day. And some estimates say that the amount of petrol and natural gas that is on the earth, inside the earth, will last another 50, 60 years. Okay, and that is assuming the amount of petrol used per year is constant, but it is not. That's increasing crazy, right? All kinds of electricity. You charge your mobile, you're actually using fossil fuel, right? Because almost 80% of the electricity comes from fossil fuel, right? Every time you charge your iPod, it's actually fossil fuel. They're getting depleted, right? So in 50 years or so, before we die mostly, right, at around of 70, or assuming an average lifespan of 70, we will see that petrol is also getting depleted. We need alternate energy sources, and as Sushovan, you can check his webpage, he's working on solar cell, for example. So there's a lot of need for harvesting energy, for storing energy, more energy efficient methods, right? So this graph, for example, it's based on the energy usage in US, okay? It shows that the total amount of energy produced in US from wind, solar and other kind of energy sources, okay, 10 times that energy produced is actually lost in converting different forms of energy from one form to another, AC to DC, DC to AC, high voltage to low voltage. If you use, for example, solar panel, it gives electricity in DC, but you need here in AC. So you need an inverter to convert from DC to AC. You have an adapter in cell phone and iPod. Your voltage is actually stepped down, right? So all this kind of, at a large scale, this voltage conversion from one form to another form, AC to DC, etc., they incur losses. That loss in United States alone is more than 10 times the amount of energy you generate using solar, hydro and water, etc., right? So huge loss. So now there's many company, one of them is Transform, okay? So what they are doing is that those losses happen because you are using silicon primarily. So they are replacing those with gallium nitride, and the efficiency has gone up to almost 99.9%. So you can cut down a huge amount of loss, right? So gallium nitride is a very critical material, and here at IISc in Center for Nanoscience also, we have a very large interdisciplinary program running on gallium nitride high power electronics, where we want to make these DC-DC kind of modules, okay? So this is a very important technological front that will be even more important in the coming years. It's estimated that the market for this will become almost a few $1 billion by 2020, okay? So in a nutshell, this is the split of the market in gallium nitride. So of course I was talking about electronics, but optoelectronics like blue LED and all is already a very big market. That's already $10 billion in 3 years back. So right now it's even more, right? So the optoelectronic market in white LED and stuff like that is very high. Power switching, and which is only $100 million market now, is expected to grow almost exponentially. And there are some futuristic applications which we will not touch here right now, but this is what gallium nitride, for example, material is right now, okay? Then gallium arsenide, indium phosphide, as I told you, have been around for almost like since 1980s, and they are still used. Actually, each and every cell phone that you have in your pocket, this is how like the basic skeleton of the interior of a cell phone looks like roughly, okay? There might be some changes here and there. So you see there is an RF and power here, right? So there is an RF power amplifier. When you send a signal to the nearest mobile tower, you have to amplify the signal and send it. When the signal comes to you, it comes very weak. It has to be amplified again. There has to be many amplifiers and low noise amplifier, power amplifier, etc. So gallium arsenide high electron mobility transistor or indium phosphide heterojunction bipolar transistor is there in each and every cell phone of the world now, okay? And without that, actually your cell phone would have been the size of a brick, because you need to handle so much of power to amplify this signal. But these are much more efficient in handling these powers and amplifying the signal at RF. Typical cell phones work at around say 2 gigahertz or so, right? So gallium arsenide indium phosphide transistors are there, and they will stay for a long time, because at low power, a cell phone doesn't work at very high power. Your low power, high speed RF kind of application, gallium arsenide indium phosphide are very important, and they are still there, and there are proper foundries, around the world. Actually, there is also in Hyderabad called GATEC, which makes these kind of chips and ICs, integrated circuits, based on gallium arsenide only, okay? And another thing with gallium arsenide indium phosphide is that they are used to make multi-junction solar cell, and the highest efficiency solar cell, although very expensive, is actually made with this material system. and they go in space. For example, in space you don't have a limitation on the cost, you have a limitation on you need to have the highest efficiency and the lightest weight, right? So they have very high importance in space application of solar cells in space, okay? And the reason why these different materials are doing so good is because of their material properties, nothing else, right? There's no black magic. So for example, gallium nitride family, I'm showing some of the material parameters with respect to silicon, for example. I'll not go in details, just look at the main thing. So the breakdown field, breakdown field is basically what is the maximum field you can apply before the material breaks down, like it becomes short. So you see silicon has 0.3 megavolt per centimeter, gallium nitride is 3 megavolt per centimeter, which is 10 times higher. So you can say that roughly gallium nitride can handle 10 times higher power than silicon for a given piece of semiconductor, right? So you can also see the indium nitride electron velocity is roughly 10 times higher. So if you make a transistor with indium nitride, theoretically it can go at least 10 times faster than silicon, right? So this material system has a lot of superior properties like high breakdown field, high velocity, and very high mobility also, right? So that's why this material system is very good for high power, high frequency applications. Also, this material system can work at really high temperatures where silicon cannot work, okay? And this is not attacked by any kind of acid and bases. So any kind of harsh environment or chemically dangerous environment, you can still use that. No acid, no base attacks these materials, okay? It's very difficult to wet etch them. You cannot etch them away, okay? That's one thing. In the arsenide phosphide family, see here I am showing you the mobility of electron, okay? I assume you know what is mobility. Mobility essentially is the slope of velocity field relation. When you accelerate an electron or a hole with field and it moves at certain velocity, what is the rate at which it goes, right? So silicon, for example, is here, right? Silicon mobility is roughly here, but I mean, of course, you can increase the silicon with some technique and by doping or non-doping. It will depend on that, but it's very difficult to get mobility of silicon which is say beyond few thousand, right? But in gallium arsenide, indium arsenide kind of material, you can have very high temperature, very high mobility. Mobility can go up to 10,000 or even more, right? So because the mobility is more, lot of the low power, low field applications can benefit tremendously from a higher mobility, right? And similarly, this is velocity of carriers as a function of gate length. Gate length is the length of the gate over which the electrons or holes move in a transistor. Okay, I'll assume you know what is a transistor. So you can see that indium arsenide, for example, has a mobility and also the velocity which is much higher than in silicon. So this is the silicon velocity, which is roughly 10 to the power 7 per centimeter per second. But materials like indium arsenide, indium gallium arsenide can have velocity which is roughly 2 to 3 times higher, right? So if your transistor gate is very small, then your speed or transit time actually depends more on velocity than on mobility. So having a higher velocity means that you can have faster transistors in a way, okay? So these are basically due to the material properties which make this material superior in some ways or the other. Now here I am showing you a picture of one of them is gallium arsenide, one of them is gallium nitride, and one of them is aluminum nitride. Can you identify which one is what? So the band gap of gallium arsenide is 1.4 eV, okay? So to give you a hint, 1.4 eV, so when will a wafer become transparent? A wafer will become transparent when all the visible light goes through it, right? Right, if your visible component of the light is blocked, then it will not be transparent. So visible, I told you, right, our eye is sensitive from around 370 nanometer to around 760 nanometer. So 370 nanometer corresponds roughly to 3.2 eV in band gap. So if your band gap is higher than 3.2 eV, then it will be transparent. If it is lower, then it will not be transparent, right? So this is gallium arsenide wafer actually, right? And this is gallium nitride wafer. You can see it's completely transparent. Aluminum nitride is even much wider. So it should also be as transparent as this, but there is some yellowish tinge that is because of some impurities, some kind of contaminants that is there, okay? So these wafers are of course routinely grown across the world. Even in our Center for Nanoscience, Professor Srinivasan Raghavan also grows gallium nitride wafers, 2-inch, okay? Maybe I'm running a little late. Alright, so let's go to epitaxial growth. How do you grow these materials? I'm going to go a little fast, okay? So this is, for example, a typical transistor stack. You have different material, unlike in silicon where you have p-dope, n-dope silicon and you have a MOSFET. In compound semiconductor, you have different layers of semiconductor, and so that you can enable a transistor function, okay? And you can see a high resolution transmission electron microscope image of different layers, for example. This is like a schematic of how you have the different layers arranged, source, drain, gate, like a 3D schematic of a transistor. Now how do you deposit these materials, right? So primarily these materials are deposited using MOCVD, metal organic chemical vapor deposition, which is like a chemical equilibrium process. It's a chemical process where you have different species that react and form the materials layer by layer. And then MBE, which is called molecular beam epitaxy, where essentially I'll show you in more details. You have a beam of molecules, they come and they fall on the surface and they grow layer by layer, okay? So But you cannot just grow randomly materials on top of each other. For example, gallium arsenide you cannot put on gallium nitride. As I told you, the lattice constant has to match up, only then you can actually mimic the crystal structure and grow. Okay. So I'll speak briefly on MBE. So MBE is molecular beam epitaxy, and what happens in MBE is that this, you see wafer over here, so there you keep the substrate. For example, you have a silicon or a sapphire substrate on which you want to grow gallium nitride. Okay. So you have a substrate here which is heated up with a coil. Okay. And these cells that you see are different elementary sources. For example, this can be a cell for gallium, this can be nitrogen, this can be indium, for example. Okay. So you have a shutter that opens and closes here. See, it's opening, it's closed, it's opening, and this whole thing is under very high vacuum. Okay, it's extremely high vacuum, and these are heated up to be in a molten temperature. Okay. So when you open this shutter, because it's very high vacuum, the mean free path is very large, so they don't collide. What happens is that because they're in molten state, they will have this beam of electrons that come out from different cells, or you can close them and stop them, of course. They will come and fall here, and then they will interact, and they will form one layer at a time. Okay. So you can control the thickness of the growing gallium nitride wafer, for example, up to 1 atomic layer at a time. Okay. So these are called cells, and you have to heat them up really high, of course. Okay, like 800 degree or even 1000 degrees Celsius, etc. Okay, that's how you deposit material. And as I told you, this has to be in very high vacuum. This, because otherwise the beams will collide and you will not get the beams will not even reach here, right? And these have to be heated up to very high temperatures, otherwise they will not give out the beam. This substrate has to be also heated up, because if it's cold, then the atoms which come here will not get energy to move around, right, and bond with each other. Okay. So this is in a nutshell the basics of MBE, and this is how the chamber looks like. Okay, these wafers that are grown in MBE, for example, this is the interior of a cross section of a chamber. So the wafer is here. Okay, that is where you are growing the sample. These are the cells that I showed you in the earlier slide. So you have different material like aluminum, indium, etc., etc. You can open and close, and it will come out. The whole system will heat up, of course, because there is a lot of heating going on. So you need cooling kind of shroud. There will be liquid nitrogen cooling or water cooling lines will be there. Okay, and then what else? So there are these ion gauges that will measure the pressure and background of the chamber. The background has to be really, really low. Okay, so I'll tell you, in ideal system, the pressure inside is 10 to the power minus 11 torr. The pressure in the atmosphere is around 760 torr. So there is a difference of 10 to the power 13 times in the pressure or in the vacuum level, that you can imagine what kind of ultra high vacuum this is. This is actually comparable to outer space. Okay, so and you load the sample and etc., and then you grow. This is a cross sectional area. Okay, and to get into such kind of high vacuum, you have to pump, right? So there are many pumps here which will keep pumping down the pressure and all the gaseous ions, and you reduce the pressure a lot. Okay, so this is what happens. Then there is one thing called reed. Okay, to be very brief, this is an electron diffraction gun like this, right? There's an electron diffraction. This is the sample that you are growing, for example, gallium arsenide or gallium nitride. There's a low angle electron gun that kind of comes here and diffracts with them, the surface atoms here, and gives a pattern like this. Okay, from this pattern actually you can identify is the surface smooth or rough, for example. Okay, so that is a very big advantage of having this reflection high energy electron diffraction scheme. As you grow the material inside the system, you can actually see what is the surface morphology, and many other things can be inferred from that. Okay, I'll show you a real MBE how it looks like. This was the MBE that I had worked on during my PhD days, and this was the day on when it was installed in 2009. Okay, so the system had just come, the wirings have not yet been hooked up. Okay, so you can see these things are the cells in which you put up the elements like gallium, indium, arsenide, nitrogen, etc. Okay, these are the cells. They're still blocked. They are not even hooked up because it was just being installed. Okay, what about? So this is the front view of the system. Okay, and then if you look from the back side, if you go towards the back side over there and looks from them there, and when you have the system installed and running, for example, this is the system is running now. Okay, so you see this red thing. This is a molten aluminum, for example, right? And this might be molten gallium. This might be molten indium. This is from the back side you view. There's a viewport like a glass. You go and looks. Okay, so these shutters are closed. See, this is a damaged shutter, so it has to be changed. Okay, so maybe gallium, indium, and other kind of materials are closed, which means their beams are not coming to the wafer, but aluminum is open, for example, right? And it is mostly at 1000 degrees or Celsius or more. So you see it's red hot, and because the shutter is open, the aluminum beams are coming out. You cannot see one molecular beam, so it's invisible here. But the substrate sits somewhere here on this side, right? So the beam comes and falls on the substrate. Okay, same thing from a different angle. So this is when the growth is going on, for example, in the chamber. Okay. What else? So I'm shamelessly advertising myself in a way because I don't have any other picture, okay, of the whole system. So this is the side view of the system. Okay. This window you see, viewport window. This was where I was showing you the aluminum molten cell. Okay, and this side is where you can stand to see the this to get this view. You have to stand here in here. Okay, you have to stand there. This chamber you see, you open the door here and you load the sample from this side. Okay, you load the sample from this side. There is a magnetic trolley kind of thing that will move the sample back here. This is the main chamber over here. Okay, this is a cryo pump that pumps down the gases more and more so that you have lower and lower pressure. Okay, and then these are liquid nitrogen lines and many other things are here. That's not going to show those things. So this is the viewport as I was showing you, where you can see the inside of the system. Okay, and the whole thing is controlled by an electronics rack. Right, this is the MB from backside. I was standing here, for example. Right, this rod you see is called transfer arm, with which you load the sample from one chamber to another chamber. Okay, and this is the electronics rack which controls all the pressure, temperature, and all the controllers of the system. Okay, these are liquid nitrogen lines that have been unplugged. Okay, for maintenance. And when I said you have to load gallium, indium, etc. as a source, you cannot just randomly load material, right? They have to be ultra high pure. So, for example, this is a cell. Okay, this is a cell which I have unplugged. We have unplugged it from the system. You see, there is some arrangement here. Okay, there is a crucible here actually. That white color thing you see, this is damaged, of course. So this is a crucible that is made out of pyrolytic boron nitride that can sustain very high temperature. And over it's damaged, of course, here. But over here inside it, you can put these materials. For example, this is pellet of gallium, or which will almost melt at room temperature. So pellets of gallium which are extremely high, 99.69%. Okay, high, very high purity gallium. You can put it here. Then you put this white case into this kind of arrangement. Okay, there are thermocouples and many other heating elements. And then you take this entire cell and plug it in the chamber that I had shown you in the beginning, right? So that's how you basically plug the source material into the chamber. Okay, and then to get this done, you have to open the system, right? You have to break the vacuum, take it out, because the vacuum inside is very high, right? So you cannot just break the vacuum. Say you have 760 torr outside here and you have 10 to the power minus 11 torr inside, which is 10 to the power 13 times lower pressure, right? You cannot just open the chamber like that. It will be a bang, like, because there is a huge difference in pressure. So you have to go step by step, and even, you know, like opening the system takes maybe days or weeks. Okay, so once you open the system, you have to wrap the system around with steel panels like this. Okay, and then heat up at around 200 or 150 degrees Celsius for 4 days. For 4 days, you heat the whole system up at 150 degrees Celsius. Why? Because no matter what you do, there is always one atomic layer of water vapor on any surface of the here. Okay, to get rid of that one atomic layer of water, you have to do this. Okay, because otherwise you cannot reach 10 to the minus 11 torr. Okay, and this is how basically the growth kinetics takes place. And I'll skip this. Basically, you have all this kind of thermodynamic processes taking place that helps you to grow. Right. So I'll come quickly to material characterization. So once you grow these materials, you cannot expect them to be perfect. Materials are never perfect. So this is, for example, the schematic of arrangement of atoms, but you see there is a missing line of atoms. So many of you might know this is called dislocation. There is a missing line of atoms, right? And these are disaster nightmares for both material scientists, also for device people, right? You have crystal imperfections. So we need to understand how these crystal imperfections are there and to what extent, you know. So for transistor kind of wafers, primarily there are 3 techniques that are done to assess the material quality. The most important being X-ray diffraction, right? So X-ray diffraction is a diffraction technique with which you can assess the thickness of the various layers, their composition, what is the quality, what is the dislocation density, is it strained or is it compression or tensile, etc. This is very easy. Atomic force microscopy, basically it looks at the surface profile at a very high resolution. And then TEM is transmission electron microscope, that you can actually see atoms in a way, right? The interfaces and the atoms, you can dislocations, you can see them, right? So those are some of the primary, these are not very important, but these are the 3 most important characteristic techniques with which you kind of characterize the transistor wafers after you grow them. Okay, so all of you probably know what is XRD, X-ray diffraction. You know Bragg's law. So you have this periodic arrangement of atoms, and at a certain angle, you have a constructive interference from these adjacent planes of atoms. The spacing between them being 2d sin theta. So you have this n lambda 2d sin theta kind of relation, Bragg law, right? So each material, depending on the atomic spacing, you will have a corresponding Bragg angle. For example, gallium nitride is 17.2 degree. So if you have a gallium nitride sample like this, for example, this is a sample and this is an X-ray source. Okay, so if you shine the X-ray at an angle of say 17.2 degree, it is theta. Then with respect to the theta, you have double 2 theta, of course. If you have a detector here, you will get a peak. Okay, that peak is because of the Bragg angle reflection, right? So in XRD, you can do a lot of different scans. For example, let me not go into the time constraint. You have rocking curve scan, which means is that you keep the detector fixed here. You move the sample such that you have the angle theta vary little bit. Okay, and you can see a peak come out at a particular Bragg angle. That will give you an idea of the material quality. What is the twist, tilt, and of the, because it's a crystal, right? Does it have grain boundary? Many other kind of information can be obtained from that. Omega to theta is a little more involved scan. Essentially, you have omega. This is omega or theta. You can call it theta also. And this to theta, right? We move them simultaneously in very small steps of degree, so that you can have a whole idea of the different layers that are there. Okay. And reciprocal space is a much more complicated step that we will skip here totally. Okay. I'll just show you how the scans look like. So, for example, this is an XRD scan of a gallium nitride, aluminum gallium nitride superlattice. Superlattice means you have gallium nitride, aluminum gallium nitride, and you repeat the layers, say 10 times or 20 times. GaN, LGaN, GaN, LGaN kind of thing. Okay. So these different peaks come because of the thickness fringes. So because you have different interfaces, your X-ray will diffract, right? So you have thickness fringes that come from the interfaces of the different layers. So one of the, for example, the red color one is what is the X-ray scan looks like, and blue color is a simulation. So you have a dynamic simulation software with which you can fit the data, and from the fitting you can extract out what is the period of the superlattice, what is the thickness of the different layer, composition, etc. Okay. And here I am showing you a scan, for example, without the fitting of just an LGaN, GaN, different kind of layers. It's not a superlattice, it's a transistor actually wafer. So these different peak positions that you see, they correspond to different layers. And the spacing between the peak positions will tell you, what is the strain state, what is the composition of the layers, etc. Okay. So this is a very powerful technique that is used to understand the crystal quality, the composition of the layers, and this is routinely done for all transistor wafers that are grown. Okay. Then you want to probe the surface, and that you do it AFM. So in your lab tour here in MNCF and NNFC here in SENS, tomorrow or maybe today afternoon you will get a tour of these different facilities. You will see an AFM. Okay. So AFM stands for atomic force microscopy. So there is essentially a cantilever like this, very small, and there is a small tip over here. You see this is the tip, right? And then there is a sample. Now you basically scan the sample with this tip. Like it can have different modes. It can have contact mode. For example, the sample will be constantly in contact with the tip, or it can have a tapping mode where it will vibrate at some kind of frequency and it will tap, it will scan, okay, as it moves. And the deflection, see the surface profile will make it deflect, right? So the deflection of the tip can be measured very precisely by a laser and a photodiode arrangement. Okay. So this deflection of the tip as it moves across the surface can be measured by the laser tip and then converted back to an image that we can see. So this is not limited by the optical diffraction limit that we are limited to, and it can provide a resolution in the Z direction which is sub-nanometer resolution. Okay. For example, this is a gallium nitride surface that I had scanned long back with AFM. You can see these atomic steps, right, which are probably a nanometer or so high, right? So these atomic steps are visible in gallium nitride surface, and the height scale is probably 3 nanometer here. Okay, and this scale is 2 by 2 micron. This area here. This is a 5 by 5 micron, for example, of indium aluminum nitride that I had grown long back. Okay, in IMD. You can see there are pits here. These dark spots are pits. It's not a very smooth surface like this. It's very rough surface and it's bad for transistor. Actually, when I had grown this sample, my advisor was not very happy with me actually. Okay. So anyways, long back. So this is also observable by AFM. You can get some kind of high resolution of the surface profile just to make sure that the surface is smooth, right? And then you have TEM. TEM is such a vast thing that it might take a few years for one to actually learn TEM. So just in a very brief nutshell, you have a sample and you have a high energy electron beam, okay, that will pass through the sample. It will be very thin. It will interact with the sample and it will pass through the sample, and you have a lot of lens arrangement to kind of magnify or project the image, and finally on a fluorescence kind of screen you have the image. And this is electron beam, so it beats the optical diffraction limit. It has its own electron diffraction limit nevertheless. So the sample has to be very thin, and the electrons have to pass through the sample so that it interacts and forms an image here. Okay, and there are a lot of different imaging modes with which you can see the sample. So for example, if I show you, so this is for example a cross-sectional view of gallium nitride, aluminum nitride, gallium nitride. See, these are almost atomic layers that you see cross-section, right? So this is one type of mode, and you see this is 2 nanometer. So this height probably is like 3-4 nanometer, right? This is dislocation. So you see, this is the substrate on which you are growing gallium nitride. Dislocations are a missing line of atoms, I told you, right? So there's a lot of junk here, a lot of dislocations are here. But as they move up, they kind of annihilate, they kind of destroy each other, and they reduce in number. Okay, that's how you want to go. You have a lot of dislocation as an interface here, and it reduces as you grow up. And this can be captured only by TEM, right? In a different imaging mode, it has captured what is the dislocation look like. Okay, this is another gallium arsenide TEM, for example. You can almost see the atoms here, right? So TEM can also have a scanning mode called scanning tunneling electron microscope, where you can actually see each atom, okay, one atom by one atom. All right, and finally, after you characterize the material for the structural quality, for interface, for surface, different kind of material aspects, you want to measure the transistor properties, right? So this is in general a schematic of a transistor. All of you know that there is a source, there is a gate, there is a drain and a gate, right? You flow the current between source and drain. You have an ohmic contact between drain and the channel, source and channel, right? And the electron gas in a typical compound semiconductor, unlike in silicon, actually there is a barrier here, no oxide here. Okay, there is no silicon dioxide or something like that. And the electron gas exists here like a 2D kind of a sea of like a water, So there is a sea of electrons here that you contact from the source and drain, right? So you want to see if a transistor is working fine or not. So there are different measurements that you have to do to see if the transistor is what you are expecting. For example, this source and drain will have a contact resistance to the channel, right? So you want to minimize the contact resistance, right? And you want to see what is the channel resistance, you want to see what is the gain of the device, which is transconductance, and you want to see what is the breakdown of the device, for example, right? So most of these characterizations are done in probe stations. Actually, we have similar probe stations in our MNCF, and tomorrow or maybe today afternoon when you have a tour, you will see that there are probe stations, and you can ask a lot of questions to the people who are giving you tour. So you have these probe tips, right? These fine tips that come down, and your sample is kept here. There's a microscope with which you look at the sample, right? And you put down the probe tips on different device pads, and then you measure. Okay. So you can do 3-point or 4-point probe measurements on the transistors. Okay. So one of the most important measurement things that you have to immediately do when you get a transistor wafer is to measure the contact and the sheet resistance, and that is done by something called TLM. It's transfer length method. Okay. So this is the top view, and this is the cross-sectional view of a TLM structure. Again, as I said, TLM is transfer length method. What happens is that you have these contact pads, right? These contact pads are there, which are spaced in different spacing. See, the spacing is increasing, right? So this is maybe 2 micron, this is 4 micron, 6 micron, 8 micron, etc. So you have a lot of different spacing, and you measure the IV between these pads subsequently, between these two pads, then these two pads, then these two, and these two, and all, and you measure the resistance. Okay. So you measure the resistance and you plot them as a function of the distance, right? So this is the distance across the pads, and this is the resistance. So further the distance, more is the resistance, right? So you have when you plot them, they will fall in a straight line. If you draw a straight line, then the slope gives you what is called sheet resistance. Okay, sheet resistance is the channel, what is the resistance of the channel, and the intercept over here gives you what is the contact resistance. Like the contact resistance is the resistance that the metal is making with the semiconductor, right? So this is contact resistance, and this is slope gives you sheet resistance. So for example, in gallium nitride, a typical good contact resistance would be around 0.1 ohm millimeter, and a sheet resistance would be between 300 to 400 ohm per square, for example. Okay, so this is the most and the first important thing that one should do when you get a transistor wafer. Okay, now this is like again a schematic of a gallium nitride transistor, for example. This is, forget about these layers. Okay, these are like for growth. This is basically the channel layer here, and this is the barrier layer. So you have electrons go from source to the channel to the drain, right? And say at zero bias of the gate, you have a channel. You have transistor operation, and this is an on state. If you want to make it off, then you apply negative bias on the gate, for example. You deplete the channel. That means you have now depleted or removed the channel below the gate, and so the electrons cannot flow, right? So this is an off state. Now when you have an off state, there might be a lot of leakage. See, the gate might leak, right? The gate is not a perfect insulator here, it might leak. That is some unwanted component of the current. Although the channel might be pinched off or depleted, but there may be channels below the actual channel, in the buffer layer, in the layers below, where you don't want to have any transport. This is called buffer leakage. So these are two unwanted components of electricity you will get in a transistor if the transistor is bad, right? So how to measure gate leakage is very easy. You put one probe here, you put one probe there, and you just measure what is the leakage, which should be very low. Okay. How do you measure this buffer leakage? For the buffer leakage, say you take two transistor structures and you etch away or remove away the region between them. Okay. If you remove the 2D, this is an electron gas, electron channel, right? If you remove the electron channel between them, you measure between this terminal and this terminal. There is no path, right, except for this. So if you see a very high current, it means that you are going through this route, which is not wanted. It means your transistor wafer is bad. If you have very low leakage, it means you have a good transistor. Okay. Then so there's something called capacitance voltage profiling that you have to do of a transistor. Okay. So for example, you have AlGaN barrier layer, you have gallium nitride channel layer, you have an ohmic and a Schottky contact, and you can do a CV. What does CV do? In a CV, you have a small signal of AC that is riding here on the Schottky, okay, and you measure the change in the charge as you're changing the voltage, right? The ratio is called capacitance. So it's like a parallel capacitor actually, right? So you see below 4.5 volt or so, the capacitance goes to 0. It means when you apply minus 4.5 volt on the Schottky here, the channel is depleted, there is no electron gas. Above that, there is suddenly an electron gas, and it's like a parallel capacitor, right? So at zero bias, for example, epsilon by d is the thickness of this layer. So epsilon by d gives you the capacitance, so you can expect the d actually here from CV also. Okay. So this is the capacitance voltage profile that is very important to understand what is the thickness and other kind of things. And if you integrate the area under this, if you integrate the area under the curve here, you get the charge density. Like what is the total charge density in the channel, right? So you see at zero bias, that is the equilibrium, the charge density is roughly around say 9 into 10 to the power 12 per centimeter square of charge. Okay. So this is very powerful technique to understand the charge profile and the depth profile of the carriers, right? And then this is basically for gain GM. Okay, what you do in GM is that you keep the source at ground, you keep the drain fixed at say 5 volt or 10 volt whatever, and you sweep the gate bias, right? You will get an ID, right? A current, right? You measure the current flowing here, and if you take the derivative of that like this, then you get something called GM. It's called transconductance. It's basically related to the gain of the device, right? So forget what is it using expensive, but you see, and again minus 4.5 volt or beyond, you have no electrons. Above that there is electron gas that is formed, and you have a finite gain here, right? Essentially, this transconductance GM divided by the capacitance of the system gives you the saturation velocity of the electrons. And saturation velocity is very important because this is the maximum frequency at which you can operate the device. The maximum frequency of operational device actually depends on saturation velocity. So you want to maximize the GM and minimize the CT. Okay, that's one thing. And this is I think the last. So this is how you measure the breakdown of a device. So this is very important. Okay, what is the breakdown voltage of a device? So you basically pinch off the channel, like you put a negative gate bias on the gate so that you have no channel, and you sweep the drain so that you are forcing the electrons to go through the buffer. Okay, you are forcing the electrons to go through the buffer, and it will break down at one point, right? So that is called the buffer breakdown. Okay, so I'll show you. This is one DAC transistor that we have measured. So the breakdown is very small. You see, it's around 15 volt, right? So we depleted the channel, and we are measuring that. We are sweeping the drain bias. We are measuring the current. You see the current suddenly spiked, right? So the buffer has broken down basically, right? Ideally, you would like to have the breakdown higher and higher, right? This is a 3-terminal breakdown measurement, and these are gallium nitride transistor wafers that we have fabricated here at SENS in our department. We have a lot of collaboration, and you can see these are individual transistors that are very big, by the way, because these are for high power applications. Okay, so if you zoom in there, you will see source, drain, gate, etc. in each of this, and these are grown on silicon wafers. Okay. So a lot of these characterizations that I have told you right now, we keep on doing them routinely to make the transistors better and better, because you know one particular thing might fail, the other might work. So until all of them works properly, we keep optimizing the device structure and the architecture layer. Okay, I think that's pretty much it, and I have probably completed just on time. So if you have any questions, I'd be glad to answer them. Okay, thank you.
Yeah. Thank you, Professor Digvijay. One or two questions?
No, silicon can be used. So there are many things over there. One is saturation velocity, right? What is the velocity of highest velocity of electrons in a material? The saturation velocity of electrons in silicon is lower than that in, for example,